All right, good morning, and let's take a look. Oh, is this working here? That's the wrong button. There we go. Okay. Yes, all right. So today we will introduce the Metropolis algorithm, or at least like some basic, very kind of like elementary form of it. Okay. And remember, what we're trying to do is we want to generate a random sample from some target distribution. And we've covered methods for it. I mean, the computer's already able to generate a bunch of random values from a lot of distributions. And then we said, we have other ways to generate random values from other distributions, like inverse CDF and rejection sampling, and there's a bunch of stuff. And so right now, it seems like we got a pretty good system on our hand. But when you move into higher dimensions, then it gets tougher to generate random samples, and so we are going to use Markov chains. Okay, so instead of generating our values independently, we'll say, you know what, we're okay with, a value being correlated to the previous values, because in the long run, eventually we'll get the distribution that we want. And so we introduced Markov chains this week, and we looked at properties of Markov chains, and we said, if a Markov chain is ergodic, all right, meaning that it is irreducible and aperiodic, then eventually it will reach its stationary distribution that we just kind of called pi right now. Okay, and so we had a couple examples of that on Wednesday, and the idea here is that so in the beginning you could start off at some bad location, but eventually it'll converge to the stationary distribution, and then when you're at the stationary distribution, you can expect the values that it generates to come from the stationary distribution. Of course, the sequence itself will not be IID, but you'll still get a bunch of random values that overall, when you look at the big picture, will come from this stationary distribution. Okay, and so coin flips are independent, and even though each individual coin flip we can't predict, in the long run we can expect 50% heads, 50% tails. Okay, with a Markov chain, each value is not independent and each value is random, and you can't fully predict what's going to happen next. But once you have kind of this stationary distribution and the limiting distribution, once you reach that, you can kind of expect in the long run the values will reflect this stationary distribution. And so what we want to do is we want to say, okay, if we can get our Markov chain to this stationary distribution, can we design our Markov chain so that the stationary distribution is the target distribution? That's what we want. Okay, we want a Markov chain so that the stationary distribution we're going to eventually reach is the target distribution that we want to generate values from. And the Metropolis algorithm is basically the recipe for designing transition probabilities of a Markov chain so that the stationary distribution of the Markov chain will be equal to your desired distribution. Okay, we're going to start off with a very basic case, like a discrete distribution, and this is trivial. It's not trivial. It illustrates how the Metropolis algorithm works. But obviously, if you have a discrete distribution, you can easily use inverse CDF method or something and generate values very simply, right? R's sample function generates values from a discrete distribution very easily. So, it's a little overkill to do the Metropolis algorithm here, but it's a good starting point. It's a good starting point for illustrating how this thing's going to work. Okay, so the example we're going to use is a discrete distribution, and it's called the island hopping example. It comes from the textbook Doing Bayesian Data Analysis. So you can read this textbook for free. The link to it is in the syllabus. It's got puppies on the cover of the textbook, and it's a good book. Okay, it's written in the context of Bayesian statistics, which again is, I would argue, kind of the primary application of Markov chain Monte Carlo. Okay, especially because you're put in these situations where your integrals are really tough to figure out. Okay, and so it says, imagine a nation consisting of islands in a chain, and a politician is going to travel from island to island trying to stay in the public eye, and at the end of each day he has to decide if he should stay at the current island, okay, or move to the island to the west, or move to the island to the east. Okay, so we got this chain of islands, and he can either do a campaign rally right here, okay, or he could go to the island over there or the island over there, all right, and have some kind of campaign event. And his goal is to visit all of the islands proportionally to their relative population. So he spends the most time at the most populated island and less time at less populated islands. Okay, so it's not electoral college where just like 7 states hold all the power, but it's he wants to kind of go to the big islands, hit all the different, cities or whatever. So basically, his target distribution of where he is, he wants to match the distribution of population, okay? Now this part, again, this is just a contrived example here. It says, unfortunately, he doesn't know the total population of the island chain, okay? However, he is able to find out the population of the island he is currently on, and he can also call up, the governor of the next door islands and figure out the population of the adjacent islands. Okay, so this is, again, kind of this silly thing. I'll draw something on the board here. All right, so we got these islands. And he's going to start, say right here, okay? And he can decide, all right, do I go to that island? Do I go to this island? Or do I just stay at my current island, okay? And he can figure out, okay, what's the population of my current island? What's the population of the islands next door? All right, so this is the algorithm. This is how he's going to make his choices. And this reflects kind of how the Metropolis algorithm is going to work, okay? Each morning, the politician flips a coin, kind of proposes an island. And he flips a coin, and if he gets heads, he's going to say, I'm going to move to the island to the west, right? If he gets tails, he'll propose the island to the right, okay, or the east, okay? So just kind of propose a nearby value. And then, so he proposes it, but then just because he proposed it doesn't necessarily mean he's going to go there, okay? And he's going to check the population of the proposed island and the population of the current island, okay? And if the proposed island has a larger population than the current island, then he'll definitely go to the proposed island, okay? But if the proposed island has a smaller population than the current island, then maybe he'll go, maybe he won't. He goes to the island probabilistically, all right? So, remember the politician wants to visit the islands proportional to their population. So yeah, if he proposes a bigger island with a higher population, he's gonna say, oh, that's an important island, I gotta go there. So if he proposes it, he's definitely gonna go there, okay? But if he proposes a smaller island, then, he's not sure if he should go or not. He doesn't want to completely ignore islands with smaller populations, okay? But also, in the long run, he'd rather stay at his current island than go to the neighboring island, right? So he's going to move there probabilistically. He's going to calculate basically the proportion or the ratio between the probability of the proposed island divided by the probability of the current island, or I guess in this case it would be the population of the proposed island divided by the population of the current island, okay? So if the proposed island is half the population of the current island, he'll go there with probability of 0.5. If the proposed island is much smaller, like 10% of the current island, you'll only go there with a probability of 10%. If the proposed island is like 90% of the current island, then he'll go there with a 90% probability, and he'll stay at the current island basically with a 10% probability. So the probability of moving there, basically once you calculate that, he'll just generate a random uniform value between 0 and 1. If that random uniform value is less than this probability of moving, he'll go there, and if not, he'll stay at the current island. And if he uses this system, in the long run, the probability that the politician is on any one of the islands will exactly match the relative population of the island, okay? So this feels like a weird system, but this system works, okay? So to illustrate how this is going to work, we'll make up an imaginary island chain with 7 islands, and I will put imaginary populations, okay? And this, we'll just keep it real simple, and we'll say island 1 has a population of 1,000, island 2 has a population of 2,000, island, so on and so forth. Island 6 has a population of 6,000, island 7 has a population of 7,000, okay? So we'll just keep it real simple. So the total population of the entire island is, what, 28,000? And basically, our target distribution is going to be 1,000 over 28,000, or 1 out of 28 here, 2 out of 28 here, so on and so forth, up to 7 out of 28, or 1/4. This is our target distribution. Okay. So that's what this is the target distribution that we want. Now we are pretending we know exactly this thing today, but again, in reality, you don't actually need to know the full island distribution. You just need to know kind of your current value and the proposed value, or at least the kind of the relative values there. But here, just to kind of make it simple, we'll just have concrete numbers that we can kind of plug in and use, okay? All right, so let's just kind of, what we're going to do is we're going to fill out our transition probability matrix P, okay? So we'll start out, we'll have kind of basically the starting island and the ending island, okay? 5, 6, all right, so 7 has to go over there. And so we'll say, okay, let's say we start off at island 4, okay? If we start off at island 4, basically, if we're at island 4, we can either end up at island 5 or island 3 or end up at island 4 back itself. There's no way to end up at island 1 or island 2, so I'm going to just go ahead and put zeros there. Island 6 is a 0, island 7 is 0. We need to figure out the probabilities. Starting off at island 4 and going to island 5, the probability of starting at island 3. We'll just have to figure out those 3 probabilities. Okay, so we'll ask, what is the probability he goes to island 5? Okay, so what's our algorithm? Our algorithm is he flips a coin, If it lands heads, which way? So what is this? East is this way, and west is this way. Okay. So if we get heads will go to the west, tails will go to the east. Okay. So he flips a coin and he'll propose island 5 if it lands tails, okay? And so the probability he proposes island 5 is 0.5. And then if he proposes island 5, he'll go there based on the proportion or the population of that island, right? So if we look at the population of island 5, it has a population of 5,000. The current island, island 4, has a population of 4,000. So if he proposes island 5, he will go there 100% of the time he proposes it, because the population of island 5 is greater than the population of island 4. So the total probability of moving from island 4 to island 5 is going to be 0.5 times 1. It's the probability of proposing island 5 times the probability of moving to island 5 given that island 5 was proposed. Probability of moving there is, if island 5 is proposed, is 1, because island 5 has a bigger population. So the total probability of going to island 5, probability from island 4, so P45, is going to be 0.5. Does that make sense? Okay. All right, what about going from island 4 to island 3? Okay. So he will propose island 3 with probability 0.5, okay, because we're flipping a coin. If it lands heads, he'll propose the island to the west. But if he proposes island 3, he doesn't necessarily go there, because its population is 3,000. Island 4 has a population of 4,000. So the probability that he goes to island 3 is going to be the probability or the population of the proposed island divided by the probability of the current island. So we do 3 divided by 4. Okay, and so we only go there 3/4 of the time it gets proposed. Okay, and so here I wrote 3 out of 28 over 4 out of 28. Okay, but we could also just do 3,000 over 4,000. And this is going to kind of play a key role later on in the context of Bayesian statistics. You might not know that the denominator is 28, right? You might know like it's 3,000 and 4,000, but you might not know it's like 3,000 over 28,000 or 4,000 over 28,000. You just might know. But even then, you can still get 3,000 over 4,000. You'll still get the same value, 3/4. And so island 3's population relative to island 4 is 3/4. And so therefore, the total probability of moving from island 4 to island 3 is going to be the probability of proposing island 3.5 times the probability of going there if we do propose it. So 0.5 times 3/4 is 3/8, or 0.375. Okay. And that means the probability of staying at island 4 is basically whatever I have so that everything adds up to 1. So we can, so this has to add up to 1, so this has to be 18.125. I hope we can read that, right? So, you could calculate it this way as well. It's the probability of proposing island 3 times the probability of not going to island 3, plus the probability of proposing island 5 times the probability of not going to island 5. Okay, so we propose island 3 with 0.5 probability, and we don't go there with probability 1/4. And then we propose island 5 with probability 0.5. And then when we propose island 5, we definitely go there, so the probability of not going there is 0. So this just comes out to be 0.125 or 1/8 as well. Okay, but just know that your entire row has to add up to 1, so that also makes it easy. Okay, so we have these numbers, and so I filled out this part of my transition probability matrix. Okay, so we can do this with any of the other islands. Okay, what if we start off at island 1? So with island 1, we could go to the right, we could go to the left, we could remain at island 1. Okay, the probability of going to island 2 is basically we have to flip a coin and get tails. And if we propose island 2, we'll definitely 100% go there. So the probability of going to island 2 is going to be 0.5. Okay. There's no island over here. Okay. So if we propose, like if I flip whatever the side, heads or whatever, if I propose this, right? If I flip the coin, it seems silly, but we're still going to flip the coin. And if we propose the island over here, we're going to just pretend this is an island with 0 population. Okay? Basically, it's outside of the realm. We can't go there. But we'll just treat it as if it's an island with 0 population. And so the probability of proposing island 0 would be 0.5. And then the probability of moving to island 0, if we propose it, would be 0 divided by kind of my current thing. And so the probability of moving there would be 0. Right? So we'll give this a 0.5 probability. This will be a 0. And then basically everything else has to be right here. Okay? So the probability that we stay at island 1 is going to be the probability, basically everything has to add up to 1. So it's going to be 0.5, but I could also calculate it this way. Probability of proposing island 0, which is 0.5, times the probability of not moving to island 0, which is going to be a 1. Okay? Plus the probability of proposing island 2, but not moving there. So 0.5. So here, I'm going to put 0.5, 0.5, the probability of going to island 2 is 0.5, the probability I stay at island 1 is 0.5, and then 0 probabilities everywhere else. All right. Do you want to try row 7? This is asking too much at 8:21 in the morning. All right, here, let me give you your first view quiz answer. First answer is B. B as in bear. B. All right, so let's look at this. Okay. What's the probability of, let's go from 7 to, I mean, this, we can make this easy, right? 5, 6, 7. All right, so the probability of going from 7 down to 1, 2, 3, 4, or 5 is all 0. 1, 2, 3, 4, or 5. So we just really need to figure out what's the probability of going to island 6? What's the probability of staying at island 7? Okay. What's the probability I would go from 7 to 6? First, I have to propose it. I would propose it with probability 0.5. And then if I propose island 6, what's the probability I would go there? Six over seven, right? So the probability I go there, so first I have to propose it, 0.5, so this is the probability of proposing, propose island 6, and then the probability of going there, and so we'll say going, given that it was proposed, this is 6 over 7, okay? So overall, 0.5 times 6 over 7, we're going to get 3 over 7. Oh, that was starting at island. Okay, here we go. Okay, starting at island 7. So the probability he goes to island 6 is going to be 3 over 7. 0.5 times 6 over 7, 3 over 7. Okay, what's the probability we go to the right? 0, okay? Because we could propose island 8, which doesn't exist. So we'll treat it like it has a population of 0. Basically, this is outside the support of our distribution. We propose it with probability 0.5. We go there with probability 0. So this is 3/7. Okay, well, we know everything, it has to add up to 1, so this is just going to be 4/7. But we can also calculate it this way. And the probability of staying at island 7 is basically the probability of proposing island 8 but not going there, which is 100% of the time I propose it. So I would stay at island 7 basically every time I flip whatever tails, okay, I would stay there. But in addition, I stay there more than half the time because sometimes I propose island 6, but I just don't go to island 6, okay? So I propose island 6 1/2 the time, but I don't go to island 6 1 minus 6/7, 1/7 of the time. So basically I get 1/2 plus 1/14, 8/14, or 4/7. So that's going to be the probability I remain at island 7. Yeah, if I start at island 7, that's the probability I remain at island 7. Okay. Here are the calculations for island 2. So island 2, we would go to island 3 with probability 0.5. If I propose island 3, it's got a bigger population. I'm going to go there 100% of the time. I go there with probability 0.5. If I propose island 1, I go there with probability 1,000 over 2,000, 1/2. So I propose it with probability 0.5, and then if I do propose it, I go there with probability 0.5. Therefore, the total probability of going from island 2 to island 1 is 0.5 times 0.5, or 1/4. And then the probability I stay at island 2, just knowing that everything has to add up to 1, is also going to be 0.25. So from island 2, I cannot go to islands 4, 5, 6, or 7. But I can go to island 3. That's going to happen with probability 0.5. I go to island 1 with probability 0.25. And I stay at island 2 with probability 0.25 as well. Okay, and so we could go through and figure out all of these transition probabilities. This is a reasonable exercise that you should try out for yourself. It's only week 5, and I know you guys are taking midterms and stuff, but we got a midterm scheduled a couple weeks from now, week 7, and there might be a problem where you have to create your transition probability matrix based on something kind of like this, all right? So as an exercise, the answers are here, but you should go through and try to make sure you can figure out these other rows yourself, okay? And I think it's relatively straightforward, but you can see going from island 1 to island 2, probability 0.5, 2 to 3 is 0.5, 3 to 4 is 0.5. Well, this is a 0 right here. 4 to 5 is 0.5, 5 to 6 is 0.5. These are all 0.5s, and then there's no probability here, so it just kind of gets pushed into the probability of staying at island 7, okay? And these are all the probabilities of going to the other islands, and so you can do all of these calculations, and these are all of the numbers. Here it is in fractional form, so these would be exact, and these are approximate decimal representations of those fractions. Okay, and I think I did this correctly. Everything adds up to 1 each row. All right, so that is our transition probability matrix for our Markov chain. Okay, so we have our state space. We can go anywhere from 1 through 7, and the probability of transitioning from one state to another state is described by this matrix, and if we use this matrix to generate values for a Markov chain, what I'm saying is that the stationary distribution of this Markov chain, as defined by this transition probability matrix, will be our target distribution, okay? And so we can check that. We can say, all right, well, what is the stationary distribution of the Markov chain described by this transition probability matrix, okay? So remember, the stationary distribution is the left eigenvalue of our transition probability matrix. Because we have, what we want is we have this matrix P, and we want it so that our stationary distribution times P is going to be equal to this, right? Times a scalar 1. But basically we want this times this to equal this. And so this is our left eigenvalue, or left eigenvector. And so the left eigenvector is equal to the transpose of the right eigenvector of the transpose of P. Okay, so here I'm going to take the transpose of P and get the right eigenvector of that, and then I'll transpose it back, okay? So the stationary distribution is I'm going to transpose the right eigenvector, that'll give me my left eigenvector, and then to normalize it, because when you ask for eigenvectors in R, it has a sum of squared equal to 1, but we want the sum to equal 1 itself, so we're going to just divide by the sum of the entire eigenvector, or sum of the entire vector. Okay, so if you say, hey, this is my transition matrix, okay, so this is just a reflection of this, and so in R, if you want to make a matrix, you can just bind a bunch of rows together. So that's what we've done. And I'm going to say, all right, so here's my transition probability matrix, and I just want to get the left eigenvector, which I've done here. And if you do this, this is our stationary distribution. That's what it says. Okay, and I can check and verify that this indeed is the stationary distribution by doing stationary distribution times my matrix P. And what we find is when I do the stationary distribution times the matrix P, I get back the exact same vector, okay? Saying that once we've reached this stationary distribution and I multiply by the transition probability matrix, nothing changes. This is exactly what we want. This is the stationary distribution. And then the other thing is well, we can compare this to our target distribution. Our target distribution is this, 1/28, 2/28, up to 7/28, okay? And that, I don't know the decimal values off the top of my head, but 7/28 is 1/4, and we have a 0.25 there, so that's good. And then this should be 1/28, 2/28, 3/28, 4/28, 5, and 6/28. And you know, just at first glance, it looks like that. We can verify. I can say, all right, if this is my target distribution, 1 through 7 divided by 28, I can just check to make sure everything is equal between the stationary distribution and the target distribution, and that comes back true. All equal is all approximately equal. So when you do test for equality, because of floating point numbers, you don't want to say is 0.3 equal to 0.3 because of floating point values, it comes out to be like you'll get false. But all dot equal, like it only checks if it's all equal up to like, I don't know, 7 places of decimal precision or something around there. And if it matches up to 7 or 8 places of decimal precision, then it'll say true. Okay, so here we're going to just check this vector, and indeed all of the values in the stationary distribution and all of the values in my target distribution, which are right here, they come back all equal. So our stationary distribution is indeed equal to our target distribution, which is exactly what we want. Okay, so if we said here's our transition matrix, I get the eigenvector of this transition matrix. We can see stationary times p gives me back the same vector stationary. I can check if it's equal to our target distribution, and it is. So, so mission accomplished, at least for this example here. Okay, let's try running the Markov chain. Oh, here, you know what? Let me also give you your second answer, which is the letter E. E as in elephant. E as in elephant. Okay, so let's write the code to do this. Okay, so we're going to just implement this algorithm exactly as we see it here. Okay, so we will take our current island. Okay, and so that's going to be like a 1, 2, 3, 4, 5, or 6. 1, 2, 3, 4, 5, 6, or 7, and we'll propose basically +1 or a -1 with probability 0.5. Then we're going to calculate this value p move, okay? And p move is going to be probability of the proposed island divided by the probability of the current island, okay? If the proposed island has a greater population than the current island, then the probability of moving is just going to be 1, right? Like if I'm currently at island 4 and I propose island 5, p proposed divided by p current would be 5 divided by 4, and then that would give me a p move of something greater than 1, okay? And then we'll move there based on a random value of u. I'll generate a random u. If u is less than p move, I'll go there. And if u is greater than p move, I don't go there. And then at the next iteration, I'm just going to reuse my current value x at time t. Okay, so this is what our code looks like, okay? I have a function that will tell me what value to propose. So given my current value, propose is just going to give us a proposed value. And what it's going to do is it's going to take your current value and it's going to add a +1 or a -1, okay? And sample 1 or -1, this is going to do it with 50% probability, okay? So if I plug in, propose 3, it'll return either a 2 or a 4. And then this is the probability, P of the value we give it. And basically, it's going to check if the value x is a number 1 through 7. If it is, it's going to do that value divided by 28. Okay, and if it's not, it's going to return 0. Okay, so if I plug in 8, it'll return 0. If I plug in 1, it'll give me 1/28. If I plug in 7, it'll give me 7/28. This is the target probability. Okay, we'll generate 1,000 values from this thing. I'm going to start at 4, and then we'll start at the center of the island chain, and then we'll go from there. Okay. All right. So my current value is going to be x at time t. My proposed value is I'm going to take my current value and plug it into the proposed function, and that will either be x at time t +1 or x at time t -1. My p move is going to be p proposed divided by p current, whatever that is. And then technically my p move is the minimum between 1 divided by p proposed over p current, okay? But if p move is greater than 1, then my random u is always going to be less than this quantity p proposed over p current anyway. So I don't technically have to do minimum between this and that, but anyway. So I'm going to just generate a random u. If u is less than the p move, then I will take the proposed value, and that will set it to the next value, x at time t +1, okay? And if it's not, I will just keep my current value and plug it in for x at time t +1. And then that will give me the next value, x at time t +1. And then I move to the next iteration. And then so I'm at that next iteration, right? T will increment to the next value, and we go on, so on and so forth. We let this run. And so after 1,000 iterations, I can see what my distribution looks like, okay? So with 1,000 iterations, my empirical probabilities are this. The target, this is 1/28. 1/28 is 0.0357, and I ended up there 0.028. Probability 2/28 is this 0.0714, and I ended up there 0.0680. Okay, so we have like decent matching, but not perfect alignment here. Okay, and I could just do a quick like chi-squared test to see if there's a significant difference between these proportions and what we got. And I get a p-value of 0.6, which says we don't have evidence that there's a significant difference between my proposed values and what I actually got. So I would consider that a win, okay? So I wrote close alignment. I mean, somewhat close alignment. It's not perfectly perfect as such, okay? 28 versus 35 or 36, but apparently that's not significant. Okay, here's a plot after 1,000 iterations of our empirical distribution in dark gray versus the target distribution in light gray, showing the difference there. And the ideal scenario is to have bars that are perfectly the same height, and we don't have perfectly the same height, but apparently this is not, the difference is not statistically significant. Okay, here's just kind of a to see what the chain produced. Okay, so we started off at 4, and apparently it proposed a 5, so it went there. It proposed a 6, and it went there. Then it proposed a 7, and it went. Oh no. Right here to here, there's 2 dots in a row there. So I guess we don't know what happened, but it stayed at 6. Then it went to 7, and then went back to 6. Then it went to 7, and it stayed at 7 for a few iterations in a row. Went back to 6. Went back to 7, stayed there, then went to 6, and then from 6 to 5, 5 down to 4, 4 back to 5, 5 back to 4, 4 back to 3, 3 to 4, so on and so forth. Okay, and so you kind of see the Markov chain bouncing around from state to state. Okay, and so this is these are the values that it proposed and where it ended up. Okay, and so we could see sometimes when it gets to a 7, it just ends up stuck at 7 a little bit. Okay. And that's fine. That's fine, because in the long run, we want 7 to be to show up more frequently than any of the other numbers. Okay, and it also and we have in our transition probability matrix the probability of staying at 7 is 4 7s, right? If you're at 7, so that happens, and so this is just kind of like the first 200 values in our Markov chain. And again, these are not IID values. Each value is related to the previous value. Either it is the previous value or it's one above or one below it. Okay, but that's kind of what it looks like. Okay, I could run the chain for even longer. So here I have 10 to the 5. I'm going to generate 100,000 values, letting the chain run for 100,000 iterations. Okay, this time I'm going to start the chain at 7. Does it even make a difference? Probably not. Okay, but 100,000 iterations, and this is what I get. After 100,000 iterations, I got 0.0368 versus the target of 0.0357. Here I have 0.074 versus the target of 0.0714, and so on and so forth. These look like they match pretty well. Okay, if I draw the plot, I would say these bars match even better, okay, than earlier. The dark gray versus the light gray, their heights seem very similar. Okay. However, if you run the chi-squared test, your chi-squared test gives you a p-value of something times 10 to the minus 7, okay? And this is one of the limitations of the chi-squared test. For it doesn't work when you have a really big sample, okay? The chi-squared goodness of fit test gives us very small p-value, and I don't know what the size limit for chi-squared test. What is that? There's no specific upper limit to the size of a table in a chi-squared test. However, okay, well, I don't know. basically the chi-squared test, when you have really big samples, it gives really small p-values. Like it's very sensitive to any kind of changes, because the way it's calculated is observed minus expected squared divided by expected, and if your expected number gets really big, then then it gets quite sensitive to these changes. So I don't know. Okay. Well, anyway. Oh, goodness of fit for very large sample sizes. What does it say? I collect very large samples. Okay, most reliable with roughly between 100 to 2,500 people. Okay, I feel like these people are just making up numbers, but I don't know. But that sounds about right. Empirically or anecdotally, that sounds about right. Okay, so anyway, I just said you might be better served by just kind of comparing the empirical and theoretical probabilities using your best judgment. And I'd say, yeah, it looks pretty good. I don't know. Okay. Okay. What we can also look at just like how the distribution, when you apply the transition probability matrix, approaches the target distribution here. So here, I'm going to start off with the politician starting off at island 4. Okay, so the distribution right now is he's at island 4. So 100% probability of being at island 4. And then we apply the transition probability matrix. Okay, so at the next iteration, he'll be at island 5 with probability 0.5, island 4 with probability 0.125, and island 3 with probability 0.375. So this is our distribution on day 2. Okay, so I guess just imagine, I don't know, living like we're able to see all the parallel universes, right? And so on day 1, the politician starts at island 4, but then for day 2, there's all of these different infinite choices that could have happened. And in half of them, the politician went to island 5. In 3/8 of them, he went to island 3, and then in an 1/8 of them, he stayed at island 4. Okay, and then again, watching all of these things, and then seeing, on day 3, where did he end up? Okay, so some of the politicians that went to island 5 then went to island 6. Some went from island 5 back to island 4. Some went from island 5 and stayed at island 5. Okay. With those who stayed at island 4, some went to island 5, some went to 3, and some stayed at 4. And then with those who were at 3, some went to 4, some went to 2, and some stayed at 3, right? And so if you take into account all of the different possibilities, where did they all end up next? Okay, this is the resulting distribution there. So on day 3, a quarter of them from the start ended up at island 6, okay? Some, 1/8 of them are now at island 2, some are at island 3, some are at island 4, some are at island 5, and this is what we have, okay? And then at day 4, this is our distribution. Some will end up at island 7, some are at island 1, and back to 3, so on and so forth. And we can just kind of keep repeating this process over and over, just kind of keeping track of, like, in all of these parallel universes of who ends up where and who ends up where, how does everybody end up, okay? So we keep applying the transition matrix. All I'm going to do is just going to take my distribution, multiply it by the transition probability matrix P, and then I want to kind of keep track of everything. So I'm creating a matrix with each row corresponding to a new iteration, okay? So the next row, row 5 is going to be row 4 times this, row 6 will be row 5 times this, row 7 will be row 6 times this, so on and so forth, okay? And then so at day 10, this is kind of what our distribution looks like. At day 11, day 10 versus day 11, it's a little bit different, okay? But eventually, here we're at day 20 versus day 21. We get a little bit of difference. Are they all equal? And it says, no, not quite, 0.004 difference, small difference, but it looks like staying relatively similar, okay? And then if you say, okay, what about day 99 versus day 100? And I'd say, at this point, we've kind of reached the stationary distribution, okay? So again, imagine all of these kind of parallel universes, and you see some people going from island 3 to island 4, and some going from island 4 to island 3, and what we see is we've reached kind of this state of equilibrium, where those that end up going from island 3 to island 4 is equal to the same going from island 4 to island 3, because half the time, when you're on island 3, half the time you end up going to island 4. Probability of going from island 3 to island 4. But then, if you're on island 4, you only go to island 3 0.375 of the time. Okay, and and then how often are you at island 3 versus how often are you at island 4? They all balance out, and so you kind of have this this thing of equilibrium where the amount going from here to here is the same as the amount going from the other way. So it's kind of like that, I don't know, California and New York, where you have everybody kind of flowing back and forth, except you have more than 2 states. Now you have 7 islands, and everything is kind of flowing in equilibrium between days 99 and 100 and so on and so forth. Okay, I'll go ahead and I'll give everybody the last answer. Last answer today is D. D as in dog. D as in dog. All right, well, have a great weekend. We'll see you next week. Happy November.